Hi, and welcome to the Java Collections Framework presentation. In the following sections, I will present the main principles of this framework. A collection can be seen as a type of structure that can group together objects. Each object that is present under a collection can be identified as an element. The Java Collections is an extremely powerful and flexible framework that is used to represent and manipulate collections. You can look at this framework as a set of interfaces that provide support for storing data in various formats and offers functionality such as sorting, ordering, uniqueness of elements, etc. Interfaces that we will mention as part of this course are list, set, and map, and also their corresponding concrete implemented classes. So, let's start by looking at the base interface for the Java Collections framework, that is the collection. The collection interface represents the base support in storing and manipulating a list of objects. Under the Java Collections framework, we will not find a class that directly implements this interface, but instead this interface is extended by more particular interfaces with specific functionality. List interface that keeps the order of inserting objects. Set interface that allows only unique objects to be inserted under the group of objects. Sorted set interface that allows only unique elements but also provides support for ordering the collection. Queue interface that acts similar to a queue, first in, first out. DQ interface that can be seen as both a queue, first in, first out, and the stack, last in, first out. As you can see, the collection interface is generic in the way that it needs to define its own parameters. But what does this mean? It means that you can define a collection of specific objects that we want to manipulate, string, integer, long, etc. But you can also define your custom objects such as person. There is also an important concept that we need to address, the fact that the collection interface extends the iterable interface. Using the iterable interface, we can iterate over any collection. That being said, since collection interface is the base of all collection interfaces, and it extends also the iterable interface, that means that all concrete classes under the collections framework will be able to use the iterator to iterate over its elements. Collection interface provides a group of corresponding methods that can be used in the actual concrete implementation classes for various purposes. We will list the most popular methods that are used frequently. Add inserts an element into the collection. Add all insert a specified collection in the invoking collection. Clear used to remove all elements from a collection. Remove an element from the collection. Equals checks for equality. Contains searches for an element in the collection. Size returns the number of elements in the collection. And last but not least, is empty, verifies if the collection is empty. Before moving to the collection workflow and discuss about different interfaces and concrete class implementations, we need to know that the collection interface is not synchronized. That means that all its extended interfaces and actual class implementations will not work properly under a multi-threaded environment. Now, let's go into detail and discuss about one of the most popular interface that extends collection, named list. List interface extends the collection interface and has the main characteristic that it retains the order of insertion for its objects and can also store duplicate elements. Under a list, you can control the position where you want to store a new element. Due to this reason, we can find specific methods that apply to this interface. We list a few. Add element E at position index in the list collection. Get retrieve the element from the collection that can be found at position index. remove the element from the list that is found at position specified by the index. There are also other methods that we will present under the following video as code examples. In terms of concrete class implementations, we will focus on two main classes, ArrayList and LinkedList. ArrayList represents one of the most used type of collection. This type of collection is backed by an array, has its base structure constructed by using an array. This being said, once you initialize an array list, its dimension will have the initial capacity of 10 elements. You can add elements to the array list, and if for example the list is full, it has the initial capacity full of 10 elements, and you want to add another element, the array that is used behind the scenes will increase in size with another 50% of the current array capacity. Now, for a linked list, please note that this type of structure implements the list interface, but also interfaces such as queue and dequeue, double-ended queue. In this way, we will get by default the functionality of keeping the order of elements by its index from list interface, but also we will inherit the principles from queue and dequeue. By following these concepts, a linked list can be used in places where you want to simulate the principle of LIFO, last in first out, and also FIFO, first in first out. So now, when exactly we should use an array list versus a linked list? An array list can be used in situations where we need fast iteration over a collection, whether a linked list is better on adding or removing elements from the collection. In terms of performance, there are some facts that we can review. An array list offers O of 1 complexity for adding searching for elements and O of n for removing elements from the collection. In the other case, a linked list offers O of 1 for searching removing elements and O of 1 amortized value for adding elements. Let's look on some simple examples of using the list interface under Java. So under our Java Collections project, list package, we can identify 3 different example classes. Under the ArrayList example 1, we can identify a public static void method and also a main constructor. You can see that we are instantiating an array list of strings. We can use both the array list but also the list interface to create this list. Let's use the list interface. I'm adding 3 names under the list, and you can see that we are allowed to add duplicated values. We have the ability to list the number of elements in the list using the size method. We can also remove a value from the list using the remove method that behind the scenes uses the equals method to check if that value is present in the list. We can also set a value in the list at a specified position. We can check if a value is present in the list using the contains method. Last but not least, let's iterate over the list using an iterator. We can run the application. You can see the results. Initial list size was 3. List contains the jack element. And since we remove one entry from the list, we have 2 names left. John and Jack. Let's move to the second example. We will see the equals method importance for custom implemented objects. So under the constructor, we can identify the fact that we are creating a list of persons. This is a custom implemented object. Let's take a look on his structure. It has a first name, a last name, also constructor. The equals method is commented out. Now let's add two persons in the list. We will check if Sabrina Morales is present in the list using both the contains and index of method. Since the person object does not have a properly implemented equals method, the equals method from the object class will be used, and this will check mainly if two objects are identical in terms of their reference value. In order to fix this, we need to remove the comments from the equals method on the person class. So let's do this. We are removing the comments from the equals method. Let's save and rerun the application once again. You can see that Sabrina Morales is present in the list, and we were also able to find the position of the person object in the list. Let's move to the final example. Over here, you can see that we are creating a linked list under the LinkedList example 1 constructor. This linked list has the integer type. We are adding three. We have the ability to add an integer at the beginning of the list and also add an integer at the end of the list. We can simulate a stack process using the push method and also a queue process using the offer method. Let's also iterate over the linked list. You will see the elements in order from 1 to 7. The set interface represents an unordered collection of elements objects in which duplicated values cannot be stored. In order to determine the equality of objects, the equals method needs to be used and properly overridden for custom implemented objects. There are three main concrete classes that implement the set interface. Those are HashSet, LinkedHashSet, and TreeSet. In the following sections, we will discuss each one of them in more detail. HashSet is a common structure that is used to store unique elements in a collection. However, you should keep in mind that this collection type does not guarantee the order of inserting data. For example, suppose we have a hash set of integers and we need to insert the following values into it: 1, 2, 3, 4, 5. If we want to iterate on the hash set at a later point, we can't guarantee that we will receive the same order of the elements as we used to insert them. An important aspect to be aware of is that in addition from a list where we use the equals method to verify elements for equality, HashSet uses also the hashcode method. So, let's introduce these three main concepts that are important for a HashSet. Buckets are places where we will store our objects, hashcode, and equals method. Imagine that we now want to store some persons under a HashSet, each person having a first name and a last name. Whenever we need to insert a new object under a HashSet, the first thing is that the corresponding hashcode value for that object is calculated. Based on the hashcode value, we will search on the corresponding buckets. If we were able to find the bucket, we now need to find out if we are able to add the object into the collection or not, since if you recall, HashSet allows only unique values to be inserted. At this moment, we need to introduce the equals method, such as we can identify if an object is already present in the collection or not. If it's not present, we will introduce the new object into the HashSet. Once again, a more detailed example will be presented under coding exercise. A linked HashSet uses the same principles as a HashSet uses, but in a combination with a linked list. This being said, we have the possibility to retrieve objects in the same order that we inserted them. This collection type can be used when we want to store unique objects and want to retrieve them in the same order as we inserted them. A tree set, on the other hand, is capable of storing unique elements in a sorted order. This sorting mechanism can be created using two ways. Natural order objects on the tree set collections will implement the comparable interface, or using a specific comparator. If neither of these two ways of sorting are used, basically if you don't specify a sorting way for the tree set, we will receive a runtime exception on adding the first element to the collection. There is a specific difference between a tree set and the other concrete classes that implement the set interface, HashSet and linked HashSet. While the later two are using the equals method to check objects for equality, TreeSet uses the compare to method from the comparable interface or the compare method from the comparator interface, depending on which type of sorting will be used. We will identify these cases while we will present this collection under a coding example. If we want to focus on performance, a HashSet and linked HashSet offers constant time performance for adding, searching, and removing elements, whether TreeSet offers log n time performance due to the fact that this type of collection is based on a tree to store its elements. Under this section, we will see some examples of using the set interface. So we have a set package with 4 different example classes, and we will navigate first to the initial class, HashSet example 1. This class has a main method and also a constructor where we'll set up a new HashSet of car objects. Please keep in mind that since this is a HashSet, all cars should be unique. A car is defined by a model, an year. It has a constructor, a toString method, and both the hashcode and equals method are currently commented out. Initially, we'll add 3 cars under the HashSet. What we want now is to remove that command and add the 4 car into the HashSet, even if that car is the same in terms of the structure as the second value added to the HashSet for Audi. As a final step, we can iterate over the HashSet using the forEach method. You can see that currently we have 4 cars in the HashSet. This is actually wrong since we have the Audi corresponding car twice. We can fix this by removing the comments from the hashcode and the equals method on the car class. So let's do this. Now the hashcode and equals method from the car class will be used, and we will only have 3 cars added into the HashSet. The hashcode and equals method will not be used from the main object class. We can now move to the second example. Let's first clean up the console. We have a main method, a public constructor, and we are creating initially a normal array list using integer values in a corresponding order from 1 to 7. We want to take this list, the integers list, and add it as a parameter to the link hash set. In this way, we will have ordering for the link hash set. You can see that we are able to iterate data in the corresponding order similar to the integers list. Let's move to a tree set example. Under the class constructor, we will create a new tree set of integers. Now we will add 3 integers under the tree set, and we will iterate over the tree set using the for each method. You will see that the values will be ordered due to the fact that we use the integer as the type of the tree set. This is happening due to the fact that the integer implements the comparable interface. We will clear the console and move to the last example. Over this tree set example 2, you can see that we are creating a new tree set of pet objects. This is a custom implemented object that has name, type, and age fields, corresponding getter and setter methods, a constructor, and also the toString method. We will add now 3 pets under the tree set corresponding collection. As a final step, we will iterate over the tree set using the for each method. Since pet is a custom implemented object, we need a sorting mechanism for our tree set. For this, we will use a comparator to compare our pets based on the age. So we will receive the pet with the age 5, 8, and 10 in this corresponding order. Map interface has different particularities from the list and set interfaces. The first thing to note is that the map interface does not extend the collection interface, so it will not inherit its corresponding methods. The next important aspect is that a map is capable of storing key value pairs, with each key being unique in the collection. Also, please note that items that are added to a map are not ordered. We'll present the following map implementations: HashMap, link HashMap, and tree map. A HashMap can be seen as a concrete implementation of a hash-based map that uses the hash value generated from its key to save and also retrieve key value pairs under the collection. Similar to HashSet, data inserted into a HashMap is not ordered. If you recall, we have seen the contains method used for both list and set interfaces. This is not a place for a map. We have in place methods such as contains key and contains value that check for the existence of a key or an appropriate value under the hash map. Method contains key uses both hashcode and equals to determine the equality of objects, whether contains value uses only the equals method. There is an important concept we need to discuss about related to adding duplicate keys. In case we want to store duplicate keys, such as we have an existing key in the map with a value and want to add the same key with a new value, the current key value will be overridden. Unlike a hash map, a link hash map follows the concepts defined under a hash map, but it also capable of keeping an insertion order similar to a link hash set. A tree map is a complete implementation for the map interface that offers also sorting functionality. The sorting is made on the keys of the collection using the natural ordering of the keys or a comparator. In terms of performance, a HashMap and LinkedHashMap have O of 1 for insertion and lookup processes, whether the tree map has O of log n or its operation at its is based on a tree structure behind the scenes. Let's look on some quick examples of using the map interface under Java. So under Java Collections project, we have a map package with 3 different classes. We'll open the first class, and you can see that under the constructor we'll create a new hash map with integer as keys and employee as values. We can now look on the employee object structure. It has a first name, last name, salary, also constructor, the equals method is commented out, and it also has a toString method. I added a bunch of data under the hash map in no particular order. We can iterate over the hash map using the for each corresponding method. By using the contains key, we will identify if a key is present in the hash map or not. Using the contains value, we can check if a value is present in the map. We have the ability to add a key in the map, and if that key is present, the corresponding value will be overridden. Let's run the project. You can see the iteration of the map. HashMap contains key with corresponding value 4, it's true, and for the contains employee hardly green, we receive false. This is happening due to the fact that the employee object needs to override the equals method. Let's fix the issue for the employee object and remove the comments from the equals method so that we will not rely on the object equals method that is used by default to check if two employees are identical or not. This will fix our issue. Now you can see that the issue is fixed. Let's move to the second example. Over here we have a link hash map. We'll use string for the key and string for the value. We'll add some sample data over here. We can iterate over the link hash map and the keys will be ordered in the same order as we use to insert the data into the link hash map. We also have the ability to replace a key and also put a key if it's not present in the link hash map. Last but not least, we'll iterate over the link hash map. Let's run the application. You can see the first iteration contains the same order as we used to insert data. We were able to also replace a value and add a new key in the link hash map. Let's move to the final example. Under this class, we have a tree map instantiation. String will be used for the keys, and the list of integers will be used for values. adding some sample data that we can play with. Now we are able to iterate over the tree map. We can retrieve the first key, the last key. As the next step, we'll create a new tree map with a new comparator that will be used to reverse the order of the keys, the order of string keys. As a final step, we'll iterate over the new tree map. Let's see the results. As the first iteration, the string corresponding ordering will be used. We are able to extract the first key, also the last key. As a second iteration, you see that the reverse order is used to retrieve data.